Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 58th Project Euler problem. As always, I will link to the problem and my repo in the description. Let's dive in. Problem 58 is spiral primes. Starting with 1 and spiraling anti-clockwise in the following way, a square spiral with side length 7 is formed. It is interesting to note that the odd squares lie along the bottom right diagonal, but what is more interesting is that 8 out of the 13 numbers lying along both diagonals are prime. That is a ratio of 8 over 13, or 62%. Okay, so yeah, 1, 9, 25, 49, so square of 3, 5, and 7. If one complete new layer is wrapped around the spiral above, a square spiral with side length 9 will be formed. If this process is continued, what is the side length of the square spiral for which the ratio of primes along both diagonals first falls below 10%? So, basically what we're looking to do here is build out a square spiral. Every time we finish a new square of the spiral, it's going this way actually, we want to count how many diagonals there are and how many of them are prime. This is actually somewhat similar to problem number 28. Yes, I looked this up beforehand. Where starting with the number 1 and moving to the right in a clockwise direction, a 5 by 5 spiral is formed by follows. And this one, we were interested in the sums of the numbers on the diagonals. For a spiral with side length of, a spiral with a side length of 1001. So, here, since we're concerned with primes and the spiral, what I think I want to do is approach this with 2 steps. First is just figure out what all the primes are. I am going to arbitrarily pick the number million as our largest number we're going to be looking at. I could be wrong. We shall see. And then we're going to use, similar to the algorithm we used for number 28, for the rest of this problem. Go ahead and pull this up like this. So if we go to VS Code, so here's what I had for problem 28. Go ahead and make our problem 58 file. Okay, so we're looking for a counterclockwise spiral. Problem 28 is a clockwise spiral. what did we do here? So here, what I did is we start with the value of 1 and an add value of 2. So, why did I do this? Because the first value that is on the diagonal is 3, and then we add 2 and 2 and 2. And then the next value we add 4 and 4 and 4 and 4. And then we would add 6, and so on and so on and so on. So how I've written the code here is sum plus equals add value times 10, and then value times 4. So it's going to be a little bit different, but I'm going to go ahead and roll with something similar to this. We don't want the sum in this next solution. Go ahead and cut down that. And for right now, I'm actually going to build this part out first. What we're going to do is we're going to go up to 49, and then we're going to print out this array and make sure we have the correct answer. So I'm going to change the limit to 7. And diagonal nums is an array. And we're going to do so 1 is on the diagonal. So diagonal nums dot append value. And then actually, I'm going to go ahead and start this with the number 1. This is just a simple do this 4 times. Value plus equals add val. So this will be 3. So it'll add, or this will add 2, so it'll be 3, and then 5, and then 7. And then after we do that 4 times, we want to add 2 to the add value. So let's see if this gives us the correct list. Because if it does, it should then be trivial to finish off with the rest of it. Okay, so here we've got 1, 3, 5, 7, 9. There we go. 1, 3, 5, 7, 9. 13, 17, 21, 25, 31, 37, 43, 49. Okay, so we proved out the concept that we can find the numbers that find these diagonal numbers. And then now let's work on making our primes. So primes equals, let's see, I think it's true, and I want that to be times biggest val. And then I'm going to have to look up how I've done this primes thing in the past. Let's look at how I did it most recently. Okay, so I want to do this +1, I'm sure. And I'm going to go ahead and grab this chunk of code. I'll rename it to his prime, sure. Line is also important. So in this case we want biggest val instead of limit. And what this will do is it's using the sieve of Eris of Eratosthenes to go through and find all of the prime numbers up to, in this case it would be up to 49. And what we're going to do is, in diagonal primes we're going to count num prime, or diagonal nums, we're going to count num primes is equal to 0 for num in diagonal nums if is prime num primes plus equals to 1. So literally just counting the number of primes in our list of the numbers on the diagonal, and then what we can do is say found num primes diagonal numbers. And this time it'll print out, it should print out 8 and 13. Okay, so that part is correct. And now we just have to do this part where we figure out where does it first fall below 10%. I'm bumping this limit up to 1001 because that'll get us roughly to 1 million, I think. And this part is going to move over. So that'll be within the while loop now. And now, let's see. Percentage primes is equal to the number of primes divided by the length of the diagonal nums array. And then times 100 to make it an actual percentage. And then if percentage primes is less than 10, print out that break. And then how do we know the length of the side here? Start it at 0 instead, so I can have this in front of this for loop. So that here I can just say sides of length add val plus 1. I already increased the limit. Let's see what we say. Okay, so we hit the limit without hitting our condition. Which means I'm going to add a 0 here. Okay, so this is taking significantly longer, of course, because we're dealing with a lot more numbers. And let's see if it deals with itself in under a minute here. I actually don't want that space there. That's just a little minor thing. And I don't actually know... Yeah, because it's all the odd numbers. And again, we did not meet our condition of percentage primes being less than 10. I'm gonna say here, if add val plus 1 is equal to limit, well, so I can keep myself honest. And I'm just gonna run the exact same thing again. Oh, it doesn't like it when I do that, apparently. That's okay. And it is going to take most of a minute to run. We know that from our previous runs. I'm wondering if maybe having this limit here isn't the best of plans. Because we are taking a bit too long to figure this out. Ah. Okay, I could be doing this part a little more efficiently. Okay, so found 2,250 primes out of 2,000 or 20,001 diagonal numbers for a percentage of. There needs to be an F here. Okay, so I'm gonna have this do this. So if I set num primes up here, and then say if is prime value, then I can put this line there, and I don't have to go through this entire array again. And that should save us a little bit on time. Let's find out. It still looks like it's taking a significant amount of time, but let's see. Okay. So yeah, we're down to a percentage of 11.25, which is about right. So I don't think we need to bump this limit up by a factor of 10. I'm going to bump it up by a factor of 2. Roughly. And let's see if we actually get an answer. So, fixing that thing where I was going through every single number multiple times did reduce our runtime to about 35 seconds, or 33 seconds instead of our previous runtime, which was about 40 seconds. So not huge savings, but a little bit. And then the goal, of course, is to take out this line, which should speed us up a tiny bit as well. Okay, this is maybe taking longer than our allotted minute time limit. And I'm not entirely certain where the slowdown is yet. I do want to go ahead and let this play out. But let's look at this and see if we can find a better way to not have this go quite so slowly. Let's see. Oh, goodness. Obviously, this is taking an extremely long time. It's already been running for a couple of minutes, so I might have to call it. Oh! Okay, so it did take over 2 minutes, but we still haven't gone below 10%. Whew. I'm gonna go ahead and try for 3001, and then just let that run for a couple of minutes while I think about how long this... What's a good way to reduce this, perhaps? I'm not sure... Oh, you know what? Instead of this... diagonals equals 1. I don't know if that was beat us up very much, but should help a little bit. At the very least, we'd be using less memory, so I'm gonna go ahead and do the keyboard interrupt thing and start it over again. It will take another couple of minutes to finish, I believe. And actually kill that, delete this part. Just letting it run for a couple of minutes while I think here. Because obviously it's taking too long to run. We want to find a way to maximize this. Here's one thing we can do, is we can take this and just add 4 every loop, because that's going to be true. I don't quite know if we can get away from this. And also, I don't know that this gives us any savings, actually. So here, I actually was doing it... I was adding 20 and... Or, like, for the first loop, I added 20 and 4. Which is... I don't know if that particular thing would necessarily be helpful here. I mean, it feels like having this inner loop is giving us some trouble, but realistically, I don't think so. I bet the slowdown is this. Although that works pretty quickly, it's still something. So now it's been running for like 3 minutes. So clearly taking much longer the bigger that we make the limit. So we might need a better way of doing these things. But I still kind of want to let it run because I'm willing to bet we have our correct answer after this run. Although I could be wrong. While still trying to think about, like, what can we do to make things more efficient? And also, realistically, like, I added this so I could see where the slowdown was if we let this continue here. And I'm kind of wondering if maybe I shouldn't just stop it now. Just so I know, like, where's the problems? Yeah, I'm calling it. Okay, so what I want to know is how long does it take to even go through this first part of finding all of these prime numbers for this. And realistically, this should probably be a while true loop. The problem is finding all of these primes in an efficient manner. This is obviously, like, this is one of the most efficient ways of finding primes that there is, and what we're learning here is it is not efficient enough for this problem. So, because as you can see, it's been a minute already, and we haven't hit this line. So this is our slowdown. So maybe instead of finding all of the possible primes first, we want to do this, take a different approach here, and just have a way of figuring out whether a number is prime that is less all of these numbers. Because we're not checking every number, we're just checking this subset of numbers. So, let's see. Go back to just problem 3. Okay, so here we did the way where we did an array. We don't want to use this method. And I think we've used this method repeatedly throughout these various problems in this series. Looks like it. And here's where we first used the sieve. But what we actually want for problem 58 here is we don't care about whether all of these numbers are prime. We care about whether an individual number is prime. And this is going to cause some issues maybe, but... So, is prime. In order to find if a number is prime, we go for, let's see, if num is less than 2, we return false. If num equals 2, we return true. If num mod 2 is equal to 0, we return false. That's a lot of trivial cases. to get us to the point where and then where like we can check I'm just gonna say our num equals 3 here. And then for I in range, we're gonna start with 3. We're gonna go up to num plus 1. And we are going to increase by 2. So what this will do is, like, for the number 5, it'll start with 3, and then it would go up to 5, which is, or actually for the number 5, it wouldn't even go into this loop. But, like, for 9, it would start with the number 3. 3 is going to be less than our condition of the square root of 9 plus 1. So what we do here is we say if num mod I equals 0, we return false. And then if we get through that loop, we couldn't find yeah, and as you can see here, the slowdown is the primes finding. So we're gonna redo how we find the primes and see if we can get down to under a minute. I'm willing to bet this is the correct answer. But let's go ahead. We're going to delete all of that and change this to a while true loop, which obviously normally while true can get us in a lot of trouble, but at this point it shouldn't be a big deal. Okay, so let's see if this gets us to the answer faster. It might still take a very long time, but we'll be looking at 52,481 numbers. Okay. Float object cannot be interpreted as an integer. Right, I have to add this in int. Actually, I'll just wrap this part in it. Doesn't make any difference, really. Okay, so that time it ran in about 4 seconds, and it found the exact same answer as that one it just ran in 4 minutes. So obviously way faster, and I'm guessing this is our correct answer. Let's find out. And it is. So, there, it was mostly a slowdown of what's the appropriate way to find whether a number is prime for this case. Obviously, while that other algorithm is very, very good in general for finding what numbers are prime, it's only good up to a certain number. And since we don't care about all of these numbers, we can just do it this way. We can check each individual number, whether it's prime. We only have to look up to the square root for these factors, because the largest factor for any number is its square root. And then, yeah, instead of finding every single number, we just have a value that we add to find the diagonals. Starting with 2, we keep count of how many diagonals we keep count of how many of the numbers on the diagonal are prime. We keep count of how many diagonals there are. Every time we complete a square, we check what percentage of primes we have. When we get to under 10, we print out this statement just for information, and then we break and print out the length of those sides. So all set, and that's it for that one. Um, I'll see you in the next.